Hello, I'm DevPoodle. Today I'll be showing you how to make a HUD using the Godot game engine. HUD, which stands for Heads-Up Display, is the information you see while playing a game, such as health bars, mini-maps, and other miscellaneous information that's useful for the player. These are typically rendered separately from the main scene and then layered on top afterwards. In this video, I'll specifically be showing you how to create the types of HUDs that games like Metroid Prime and Lethal Company have. In these games, the HUD is a part of a physical visor attached to the player, which not only looks cool, but is also helpful for keeping the player immersed. Here's a little snippet of what our final effect will look like. The HUD will be a 2D scene rendered into a sub-viewport with a shader and script to make it appear more 3D. So, let's get into it! The first thing we need to do is set up a basic scene with a first-person controller. It's much more difficult to see how good the effect is without these. If you already have something set up, feel free to skip 2 chapters ahead to creating a 2D overlay. Anyway, let's first add a basic environment. Go up to the top bar, and add the default environment and default directional light to our scene. Then create a new Mesh Instance 3D node. I'll rename mine to Floor. Go up to the inspector and assign the mesh instance a default box mesh. Let's change its size to be 8 by 1 by 8. Right now it doesn't have any collision. A quick way to add collision to meshes in Godot is to go up to the top bar and click on Mesh. This gives us a bunch of useful tools regarding a mesh, but we're most interested in Create Collision Shape. Press this and a menu opens with a few settings telling Godot how to generate the collision. For the first option, Collision Shape Placement, we want to change it from Sibling to Static Body Child. This means the collision shape will automatically be assigned a static body and will stay attached to the mesh. For the second option, Collision Shape Type, we want to change it from Tri-Mesh to Single Convex. Tri-Mesh is good for more complicated shapes, but since our mesh is just a basic cube, Single Convex is already a perfect representation of it. Finally, we'll click Create. As you can see, our specified collider is right here under the floor mesh. To demonstrate the effect properly, it would be great to have a basic first-person controller. We'll actually need one to add parallax to the overlay, which is an effect I'll add later in the video. To keep this video short, we'll just download one from the Godot asset library. Go up to the very top of the window and click on Asset Lib. You may have to wait a little bit for this to load. In the search bar, let's search First-Person Controller. I'll download this one, Quality First-Person Controller V2. I've used it before, so I know it's a pretty good controller that has all the features we need for this demo. You can read about the features of the controller here, but it doesn't matter much in our case. So let's click Download, then click Install. Installs fairly quickly, so now we just need to go under Add-ons, FPC, and then get this character scene. This is the first-person controller we need. You can just drag and drop the scene into the demo, and playing it works perfectly fine. Alright, now that we have all the example stuff set up, we can focus on implementing the HUD. The HUD is going to be rendered using a separate scene, and to do that, we need to use a viewport. The easiest way to use a sub-viewport is to first create a sub-viewport container. So let's create a sub-viewport container. And to make sure it covers the whole screen, we'll go over to the inspector and enable stretch. Then we'll go into the 2D view, and in the anchor presets for this container, I'll choose the full rectangle option. Now we can create the actual sub-viewport as a child of this sub-viewport container. In the sub-viewport settings, make sure to enable transparent background. When this is disabled, the sub-viewport would cover the whole screen and we wouldn't be able to see any of the original scene. Now everything that's a child of the sub-viewport will be rendered overlaid on top of the screen. To make things easier to edit, I'll be making the graphics of the HUD in a separate scene. So in the file tree, right-click and create a new scene. I'll just call it HUD. I don't want to spend too much time on what's actually being displayed. That really depends on what type of game you're making. But to make it look at least a little nice, I'm going to drag in this image I've made of a visor overlay. There's a link to download this right in the description. I've based it off of the Metroid Prime visor, but it's massively simplified, of course. The sprite starts out a little big, so let's immediately shrink it in half. Then, to center a screen around it, let's add in a 2D camera to the scene. From here, the specifics are up to you. For example, we could add in text or images or other various UI elements. For now though, I think this is good enough. If we go back to the demo scene, we won't see anything yet. That's because we first need to add the HUD scene we just created as a child of the sub-viewport we created earlier. Now, if we run the scene, we have a basic overlay that follows our camera. The rest of the video is on making it appear as an actual 3D visor. First, we're going to add a shader that curves a sprite around the center of the screen, making it seem rounder. Then we're going to add a bit of parallax, making the HUD appear to move at a different speed than our camera. To add curvature to the overlay, we first need to go to the sub-viewport container and give it a custom material. This is going to be a shader material that I'll name HUD.GD shader. Let's clear out everything except for the fragment function. I'm going to create a uniform float called curvature, and I'll set its default to 4. The lower this value, the more warped the HUD will appear, and the higher the value, the more flat it will look. In the fragment function, we'll create a centered version of the default UVs. This is equivalent to scaling the screen UV by 2 and then subtracting 1 from it. We'll then create a variable representing how warped we want the UV to be, called UV offset. This is going to be equal to centered UV.yx divided by the curvature uniform we specified earlier. Finally, let's create a variable to store our distorted UVs called warped UV, and set it to the centered UV minus the centered UV times the UV offset squared. To see how this looks, we'll set the output color to be the texture of the sub-viewport container, sample that the warped UV, first added 1, and then multiplied by 2 to uncenter it. So this is what the effect looks like. And as you can see, if we pick a lower curvature, the element warps more, and if we pick a higher curvature, it flattens out. I personally like curvature in the range from 3 to 5, just to make sure not to overdo it. The final bit of polish to our HUD is going to be adding parallax. Parallax is when different layers of an image are moving at different speeds to imply some level of 3D-ness to the scene. In our case, we want the HUD to look like it's moving a little bit slower than the camera, so it feels like it's a physical object in the world rather than a static overlay. To implement this effect, go back to the HUD scene. We're going to give the scene a basic script. First, I'm going to export a node path for a character body 3D. This is going to point to the player node. Then I'll define 2 other variables. First, a head variable, which is going to be a node 3D. Second, a previous rotation variable, which is going to be a vector 2. To see what these are for, let's define the ready function for this script. The head variable is going to be set to the player's head node. In the first-person controller we're using, this node essentially is just the parent of the camera. If you're using a different first-person script, then this may be called something else. Then pre-rotation is just going to be the current rotation of the head node. So we'll do vector 2, head.rotation.y, head.rotation.x. Finally, we can define the physics process function, which is where the parallax effect will be calculated. Let's copy and paste the line in which we define the previous rotation. Except, we want this assigned to a new variable called current rotation. We'll get the sign distance between the current rotation and the previous rotation by subtracting them and storing the result in a new variable called dist. Now, instead of moving the whole HUD, we're just going to offset the camera, which will create the same effect. So $camera3d.offset. And then we're going to subtract the distance we just calculated. Let's multiply it first by delta, and then by some constant, which I'll just set to 1600. You can change this multiplier to increase or decrease how quickly the HUD will move away from the center. Let's finally update the previous rotation to be what the current rotation this frame was. Alright, so when I tried to run this, I actually ran into a mistake. What you have to do is go back to the example scene and go to HUD, and we exported the node path for the player earlier, but I forgot to actually put the character there. So just drag and drop the character from the scene tree into the exported node path, and everything should work fine now. Now, if you test this in game, you'll notice the HUD isn't following the player at all, so we're going to need to add in something to put the HUD back where it's supposed to be. So, still in the physics process function, let's set the camera's offset again at the very end. We'll lerp it between its current offset and vector2.0. Then the final parameter is going to be 1 minus pow of 0.03 to the delta power. If you haven't worked much with the lerp function, this is just mathematically how you're supposed to use it with delta time. Anyway, now if we test the parallax effect, it works. This makes the HUD feel more dynamic and like a physical part of the space. Now, there's another decision you have that I didn't mention earlier. As we currently have it, the HUD lags behind the player. But if you change the minus sign in the initial offset calculation to a plus sign, then the HUD actually moves ahead of the player. Both of these look good, so it really depends on personal preference and the type of game you're making for which one you choose to use. For example, if you know the player is going to be making a lot of quick, sporadic camera movements, then the HUD moving ahead of the player will feel more natural. But if you're going for a more slow cinematic experience, then maybe the slower HUD is more appropriate. As always, it's important to experiment with these effects. And if you're going to put this as an actual game, I'd highly recommend including a setting to disable this, to help people who have motion sickness. So here's the final effect in action. I put the character in a small demo scene so you can see what it looks like with actual gameplay. There's one last thing I want to touch on though. While this tutorial showed how to make a 2D HUD overlay, it's pretty easy to change it to use a 3D mesh instead. You just need to replace the 2D HUD scene you created with a 3D scene. You'd probably also want to get rid of the curvature shader, and you'd need to change the parallax effect to rotate a 3D camera instead of offsetting a 2D one like I did in this video. I personally think both can look really good, although as a 2D artist, I am a little biased towards a hand-drawn HUD. I hope you enjoyed watching this video and that it helped you learn more about Godot and how HUDs work in video games. I'm DevPoodle, and I hope you've had a wonderful day, and I'll see you next time. Goodbye!